Hello, so welcome to a video about bbprepared. This is a new library I've put together which contains algorithms I've used in multiple papers for preparing STK building blocks for cage construction or whatever you want to construct by picking ideal conformers for that process. It's pip installable, or you can use the instructions here to install the development environment. And while the example I showed today will be on STK examples, there's also examples in the tests that are developed with the code. So let's go through the script process together and we'll run through everything. I'm going to show 4 processes that have input into the code. There are more in there, and if you find anything particularly useful that you would like me to develop, write an issue in the GitHub. So the first process, they're all kind of put into these different Python functions, which you can probably copy and paste, and hopefully it will do the job. The first process is about finding the functional groups in a building block that are either the furthest or the closest. So if you, for example, have this building block and you are searching for this functional group, which is the carbon, nitrogen, carbon functional group factory, this will give you 3 functional groups, but you need only a 2 functional group building block. So you can either, and something I've often done is select the furthest apart functional groups, which makes sense for the problems I've been using them for, but I've provided these modifier classes which take some building block, so either the closest FGs or the furthest FGs. They have a modify method which takes some building block and some parameters and gives you a new building block with those parameters, but the structure has not changed. So in this instance, closest FGs will find 2 functional groups that are the closest, ideally these 2, or these 2. And furthest FGs should return a building block with these 2 functional groups, the furthest selected. And so we can see that when we have the original, we have 3 functional groups. The closest will give you the first functional group and its closest, and the furthest will give you the first functional group and its furthest. Cool, so that's quite simple. It becomes more complicated when you have more than 2 desired functional groups, and so always check the output for this process. A way to avoid this as well is to define your smart string here more precisely, and then you may exclude the undesired functional groups anyway. Cool. So the next thing is to use the planify method, and this will find you a conformer with the most planar structure. So for example, we have this building block, and we want to find the most planar conformer of that. So we have some helper classes for this process. We have generators, which generate ensembles of conformers which contain STK molecules. These include the RDKit ETKDG algorithm and a torsion scanner algorithm which scans selected torsions, and I'll run through that in a second. The other thing is we have the selector functions. So I'm going to quickly detour back to the GitHub for this. So we have a range of selector functions. For example, by ID selects atoms based on the IDs you provide. Deleters, not places, and binders select atoms based on the functional groups. We have the all selector. Well, it's actually 2. We have all selector and we have all non-hydrogen selector. So this is heavy atoms. And each selector actually provides a way to select atoms, so this will return atom IDs, but you can also select atom position, so this will select the atoms and then give you the positions of those atoms, or you can use the yield stepwise. And this makes more sense when we look at the by smart selector. So the smart selector takes a smart string, finds that subgroup or multiple instances of that subgroup, and allows you to select atoms from that subgroup. And you can either select all of the atoms in all of the subgroups, or you can yield each the selection from each subgroup you find. And then the final example is the XCOMX selector. This is just a way to give you the 3 positions of the 2 binding groups you have in a molecule and the centroid, and this allows you to define orientations of that molecule. Cool. So in this instance, we're using the all selector, and we're going to use the ETKDG generator and the torsion scanner generator, and I'll show you the different outputs. So when we run this, we have ETKDG, takes not very long at all, and this is the minimum score, so the score of the most planar conformer. Whereas if we run it for 12 seconds longer using the torsion scan over rotatable bonds, carbon-carbon bonds, which is given by this smart string, if we run the torsion scan over that, it takes a lot longer, but we get a more planar conformer. And we can see that if we look at the ETKDG output versus the scan output. So the cost versus target is something to consider. Otherwise, the actual code is the same. So you have a generator, provide it to, this provides you an ensemble, and then you have a process, which is some class that takes your ensemble and your selector, and you can use that to get the minimum. So this will give you the conformer that is minimum scoring. You can calculate the scores for any molecule, and the process will actually contain the data as it goes. So there is some possibility that if you use a process for a very long time, it grows in memory. But every time you redefine the process, you have a new data set, and so it will try and cache that. Cool. The next thing is to use the torsion process. And so if we have a molecule like this, we basically want to take the nitrogen, carbon, carbon, nitrogen torsion and find conformers that target different values. So in this instance, so this is the torsion here we want to target, and we can use the by smart selector and the torsion scanner generator. We generate one ensemble, but we have 2 different processes with either target 1 or process target 2 as 120 degrees or 60 degrees. And when we run this, you can see it doesn't take very long because there's only one torsion to scan. We get target 1 with a torsion of 120, or target 2 with a torsion of 60. Cool. And then the final thing is the ditopic fitter. So in this instance, you have a molecule like so, and you want the binding groups to point the same way. The ditopic fitter process will take your ensemble as per usual and generate such a molecule. Well, the best it can, given the ensemble you provided. And that's shown here. Cool. So you can see that doesn't take very long, and now that was all. So thank you for watching, and if there are any issues, please let me know.